Alright, phase diagrams. Okay, a phase diagram is a graph of pressure versus temperature that shows in which basically a phase exists under different types of conditions. So a familiar kind of phase diagram you'll have is for water, which you can see in this little graph. So it's going to be more often than not, hopefully a colorful one. If not, it'll just be a bunch of lines. Okay, before we move on, we gotta define a few terms. So a triple point is the point on which a phase diagram that represents the temperature and pressure at which three phases can coexist, and we'll point that out shortly. What that means. Critical point is the temperature and pressure at which a substance cannot exist as a liquid, and then we have another definition called normal boiling point, which means the temperature at which a substance boils at 1 atm. Okay, so this is a very common substance, water, and there's a lot of information that can be drawn from this phase diagram. So here we have our solids right here, liquid phase, and then our gaseous are more commonly known as the vapor phase. Okay, that triple point that we mentioned before is right here. It is basically the point at which three different states of matter can coexist at the same time. So if you're at this point, that means you are looking at a container of, let's say, ice, water vapor, and water all existing at the same time. Neither one of them is transferring to the other. I mean, they are, but it's at basically equilibrium. It's a very rare occurrence for that to happen, but that's in theory what is happening at a triple point. The critical point is the point at which basically it can only exist as a gas beyond this point. So on this graph, the critical temperature is 373.99. If I increase the temperature to 1,000 degrees Celsius, then there's no way water vapor is going to ever turn into a liquid. It's got way too much energy. There's no way that the water molecules will stick to form a liquid. So critical temperature, anything beyond the critical temperature, it's only going to be a vapor. Same goes with the critical pressure. This is the critical pressure at which it can only exist. It begins. The possibility of it forming a liquid is at this point. So critical pressure and critical temperature for water is going to be located on the farthest right point of the graph, whatever graph you're looking at. The other term that we had was called normal boiling point. Basically, normal boiling point and associated with normal freezing point is that point on the graph when the pressure is 1 atm. It is the freezing and melting point of a substance. So water is a very familiar one. We know at 0 degrees Celsius and at 1 atm, ice will and water will be right there in that state. Same goes for when you're going from a liquid to a gas. At 100 degrees Celsius, we are now transitioning between liquid and a gas. Okay, just to give you a different phase diagram, this is a phase diagram for a very common element that people like, and it's diamonds. So here the temperature is in Kelvin and the pressure is in pascals, and this actually has four phases. It's got graphite, diamonds, which will be eye opener, liquid, so carbon can actually have liquid carbon, and you can also have gaseous carbon. But if you take a look, the temperatures will be very, very super hot, which probably means you probably won't be around to see that if you are actually looking at gaseous carbon. Extremely, extremely hot temperatures and extremely, extremely large pressures. So the unique property of diamond is that diamond forms at very, very high temperatures, so anywhere between 0 and 4,000, less than 4,000. And very, very, very high pressures. So diamond is a very rare element on Earth. It happens at a very specific, unique conditions on the planet, and it's one of the rarest elements that you can find on the planet. So just to give you a different idea of a phase diagram of a different element. Every element, every compound has its own phase diagram, and it's going to look different, different compared to each one. Okay, we're going to just kind of interpret a phase diagram and talk about some of the things we can draw just from this phase diagram. So let's create a scenario where I'm going to be, let's say we're at 1 atm and we're at 50 degrees Celsius. So let's say we're right there on the phase diagram. I'm going to have a piston, and the piston head can move because that's going to help me control my pressure. And I have a Bunsen burner so I can heat this up. So at this point, I am all liquid in this piston. So let me draw my liquid here. So in here it's all liquid. It's all in this piston head at that pressure and that temperature. Okay, there is actually two ways that I can make that liquid turn into a gas, and I can change my pressure and my temperature. One of the things I could do is, let me change the color of my pen, is I can actually just lower my pressure. So if you notice, if I just lower my pressure and keep my temperature constant, I can actually make it into a gas without having to increase temperature. Well, how would I do that? I'm going to basically take my piston head over here, and since it's movable, I'm going to lift this. And since I'm lifting this, I'm increasing my volume, I'm lowering my pressure. In theory, all of this liquid water in here will all turn into a gas because I've lowered my pressure so much, close to almost zero pressure, that this will all become a liquid in here. So once we get to a certain point, let's say we get to 0.1 atm, then this will be all gas in here and no liquid. Because I've raised my piston head so high, I'm able to convert it to a gas without having to affect temperature at all. So you can technically boil water without having to heat it up. Well, the more common way for us to make a liquid into a water is to basically heat it up. So if we go to my point right here, and so we're still at this point, the other way we can do this is to actually increase the temperature on this. So if I increase temperature but my piston head is locked, it is not movable, then again I can make the water in here turn into a liquid by just increasing the temperature inside this piston, but the piston head is not movable at this point. So that's one way we can make water turn into a gas very easily. Okay, another scenario that we can discuss is what happens if we had solid ice. So let's say we're at this point, it's 1 atm and we are at negative 20 degrees Celsius. And here I have a block. Basically all my water is in ice at that pressure and that temperature. Well, we can make water sublime, which means it goes from the solid to the gaseous state with skipping the liquid. And the way I can do that is by lowering my pressure. So if you notice here, if I lower my pressure, it goes from a solid to a gas, and it completely skips the liquid phase. And I can do this at a very low temperature. So as long as my temperature is below 0 degrees Celsius, I just increase my piston head, lower my pressure, and all this ice will turn automatically into a gas at those conditions. And this is exactly how kind of dry ice works. Dry ice is not water, but it's carbon dioxide, and at our pressure and temperature, which we're comfortable with, dry ice sublimes. It actually goes from a solid to a liquid. Okay, so here is the phase diagram for dry ice. Of course, when you buy dry ice, it's super cold. So here my temperature's in 0 Celsius here, atm here. So when you buy it, it's very cold, and we normally live around 1 atm. The minute you put that in room temperature, it's going to turn into dry ice, and you'll see it. If you ever get a chance to play with it, it's fun stuff. Just make sure you don't touch it because it'll burn your hands. But that's exactly what dry ice does. It's going straight from a solid to a gas. Okay, so I hope you helps out with phase diagrams.